In terms of power and equipment needed, most hams recognize that Morse code is one of the most efficient ways to communicate. So, when weight, size, and cost are important, Morse code, or CW, is often the mode of choice. However, on the human side, when sent and received using traditional methods, there's a steep and often long learning curve that has to be cleared before its hardware advantages can be realized. So, if operating CW is a new venture to you, but you don't want to spend months cloistered away from the family mastering a skill that may not, at the end of the day, be your cup of tea, but still want to experience firsthand its possibilities, or if you fall into the group that some of us find ourselves on the high end of the age continuum and now have physical issues getting in the way, or maybe you're a scout or school club leader looking for a project that blends both history and new technologies to spark the interest of next generation creative thinkers in your charge. Or maybe none of the above apply and you're just looking for something beyond a blinking LED to demo the power of a $10 ESP32 and have an afternoon or evening with nothing scheduled. Then this project might be for you. So forget the shortcomings of the presenter and focus on the merits of the project itself. And to you who have watched this channel before, yes, in many ways this is a repeat of two earlier projects. But what's significant here is this iteration combines both sending and receiving into a single seamless package, effectively having the cost, time, and space needed to replicate its predecessors. And as such, I felt warranted its own video. Now, out of the other side of my mouth, because so much of it is replication of the two earlier projects, I'll skip much of the detail found in their videos and leave it to those who care to check them out. So that's the why behind this video. Now let's look at what it is and what is needed. On the what it's needed, there are two major components. As you can guess by title, you'll need an ESP32 WRROM dev board, the 30-pin version. I repeat, the 30-pin version, so count twice before hitting the buy button. And at the time of this video, I found a US vendor selling them at $6.19 with free shipping. The second, and currently the most expensive part of the project, is the 480 by 320 ILI 9488 TFT display with 4-wire SPI interface. Those are currently selling for around $15 to $20 US. Now, this project does not use a touch interface, but strangely, from some vendors, the touch version is the cheaper offering. If that's the case for your vendor, then buy it. Now, on the build side, just to see it work, it's pretty easy to breadboard this project, but a more permanent and, in my opinion, really the easier way to go is to use the PCB files found at the GitHub site and order a board from JLC PCB or the like. And if you have access to a 3D printer, there are also STL files to make a custom case for it as well. If you go the PCB route, then to key your transmitter, you'll need a D4184 MOSFET and for onboard side tone, an HYDZ piezo style buzzer. These, when bought in quantity, are like $1 or less items, but may cost a bit more if purchased singly. Also, a word about the buzzer. It's really only needed in standalone mode for testing or demoing the keyboard side of the project. Typically, in a real QSO with a unit connected to your transceiver, the radio will generate the side tone you'll be listening to. So, while I have the buzzer installed, I have a piece of masking tape covering the little hole where the sound comes out to mute it to almost to the point where I don't hear it. To further isolate the ESP32 from an external key connection, the PCB Build uses a 2N3906 and 3904. If you choose to breadboard the project, you might design your own interface to take advantage of what you have on hand. There's nothing special about my design. At the end of the day, it's just a switch. The main thing to make sure is your solution doesn't let the ESP's I/O pin see anything more than ground and the ESP's 3.3 volt rail. On the decoder side of the project, you'll need to decide how you want to link your audio source, typically the output of your receiver. When demoing the decoder, I often use one of these little microphones. It works well enough, and because it requires no electrical connection, it's a foolproof way to get things going. But for serious work, I prefer a hardwired connection. The processor works well with a 2-volt peak-to-peak signal, but the incoming audio needs to be AC coupled, and it needs to be biased midway between ground and the 3.3 volt rail. So I use this simple network to connect my receiver to the decoder's input pin on the ESP32. At the time of this video, the PCB version is not provisioned for decoder input, so you'll need to tack in this network similar to what I've done here. The last thing to say about the PCB is its provision for a 7805 regulator and a reverse polarity protection diode. It's there for those who want to power the unit from something other than 5 volts DC. But in my shack, a USB 5 volt source is readily available, so I don't have these components installed and instead power mine via the ESP32's USB connector. When the unit is linked to a Bluetooth keyboard, current demand at 5 volts is approximately 150 milliamps. So, assuming you wanted to build a self-contained battery-backed POTA-SOTA version, a single 18650 working through a boost converter should be able to power this project for several hours. Now, for some, the big challenge in this project will be programming or actually flashing the ESP32. In the Send Morse Code with Bluetooth keyboard and ESP32 video, starting at about the 5-minute mark, I detail the steps needed when using the project source code. The steps shown there are identical for this version, so if you want to work with the source code and compile your own bin file, that video should walk you through the process. But for those who just want to have a working unit, the by far easier way to go is use a flash loader and the precompiled bin file found at the GitHub site. There are links to both the bin file and the flash loader in the GitHub's readme.md file. It's a pretty straightforward process that uses a standard USB cable to pass the bin file from your computer to the ESP32. Windows users might need to install the CP210X driver for the ESP32. If you do, then watch around the 6-minute mark in the video for the process to install this driver. So that covers the project build. Now let's look at how, where this combined version differs from its parent projects. On the CW Send side, at the source code level, numerous tweaks have been made, but from the user's perspective, I want to say there's essentially no change. So for a detailed walkthrough of pairing and sending CW with the keyboard, watch the Bluetooth keyboard video at about the 13:30-minute mark. I like to think it's basically a type it and it'll send it process, but there are a few special keys that hopefully you'll find to be labor savers, leaving more time to focus on the conversational side of the QSO. On the decoder side, it would be nice to say, if you can hear a station, the decoder will convert it to text. Well, that can be true, but for that to happen, the incoming signal has to satisfy 3 conditions. First, it has to be within the frequency range of the tone detector, 600 to 850 Hz, with 750 Hz being ideal, and second, be at least 1 S unit, preferably 2, above the noise floor. Because the noise floor represents 5 of the 7 digital states of CW, it can't copy signals below the noise floor. Now, you can do things to lower the noise floor, for example, quieter antennas and narrower passband filters. From watching literally hours of scope views of HFCW transmissions, it's amazing how quickly a signal can dip in and out of this minimum signal criterion. Morse code contains no error correcting check bits, so miss one dit or mangle a DAW and the character converter is hosed. Now, assuming the signal passes the first two conditions, the third hurdle is timing. Very few ops send so poorly that the decoder can't differentiate their dits from DAWs. But space timing is a whole other story. As said, the space can represent one of 5 conditions or states. If it lasts long enough, then it means there's nothing to decode. Okay, that state is easy enough. Next, if the loss of signal is on the order of the length of a dit, then its meaning is to continue to build on the current symbol set. So we need to add the following element, be it a dit or a DAW, to the set. That's state 2. But if loss of signal persists for around 3 dit intervals, then we're at state 3, the end of character signal, and it's time to convert the current symbol set to a character. And by the way, start a new symbol set. Now, if the loss of signal persists for something like 7 dit intervals, then we've arrived at state 4, a word break, and it's time to insert a space in our decoded text. And finally, there's state 5, loss of signal due to noise, QRN. Here the decoder needs to recognize it for what it is, ignore it, and continue to act as if the far end is still sending a carrier to form the current dit or DAW. With machine set code and a strong signal, detecting these 5 states is fairly trivial, and generally not that difficult with the majority of ops using a simple straight key, because with a straight key all space timing is created using the same force. The challenge comes with semi-automatic mechanisms. With these, the force needed to create a space differs with whether the space occurs between 2 dits, 2 DAWs, a dit-to-DAW transition, or vice versa. So to convey just the inner element timing, 4 muscle memories are needed. And remember, we just said a word will typically be formed using 3 distinct space timings, so it can take up to 12 muscle memories to generate all possible timing combinations needed to form a word. And arguably, the muscle memory count is greater than 12 when different consecutive dit strings are taken into consideration. But I digress. The point is, space timing, as important as it is often the poorest managed component in a CW transmission. To compensate, or maybe the better way of saying it, to extend the decoder's accuracy in parsing the space state, the decoder has 4 what I call decode modes. At this time, the decode mode in play is selected manually using the Control plus D key combo. Which way you index through the 4 modes is controlled by using either the left or right control key. And that breaks a point to note about this decoder versus its parent project. Previous decoders made use of a touchscreen to change settings. This version, all decoder setting changes are done via the keyboard. Now, back to the decode modes. The first, the default mode, is labeled NRM, as seen here at the bottom of the status line for normal. This setting will be your best choice for 90% of the signals found across the bands, and definitely the one to be using with machine sent code. But that said, all decode modes should give decent results with strong machine generated CW. Now, before we go chasing the other decode modes, it's important to first confirm that the tone decoder is happy, and second, that the decoder has adapted to the speed, the WPM, of the sending station. To confirm, the decoder state, look at the far right bottom corner of the display. With each far-end key closure, you should see a solid green square. If it flickers while the key is down, then likely the signal is too weak to be decoded reliably. Check your S meter and verify you're seeing at least a 2-unit bump above your noise floor. On the other hand, if the square is white, you're overdriving the tone detector and need to reduce the input audio. Finally, if the square is blue or red, then the input tone is too high or low. Blue for high, red for low. For best decoding, refine your receive frequency settings so that the tuning indicator is green. Given that the green square is tracking what you're hearing, move your attention to the right of the tone indicator to the WPM reading. It's normal for it to be changing, but the first value, the one in front of the slash mark, needs to be fairly close to the far end sending speed. It's self-adjusting, so there's nothing for you to do except wait for it to get to where it needs to be. After a little bit of listening experience, you'll develop a sense of what's right for what you're hearing. If you want some over-the-air checks, listen to W1AW. Except for weekends, they run bulletins and practice sessions several times daily. Bulletins are sent around at a constant 18 words per minute, and the practice sessions can range from 5 to 35 words per minute. But not all sessions span these limits. Google W1AW for more info on frequency, time, and speeds. The last point to note about the WPM reading is after the slash mark, the decimal value shown is the received dit to da ratio. Ideally, it would read 3, but plus or minus a couple of tenths is close enough. It's info only, but can help you identify what kind of fist or key you're dealing with. Now, to the right of the WPM reading, you see a frequency value. If the decoder is set to AF, auto frequency, mode, then the value shown is the frequency of the incoming side tone. And even though the tone you're hearing has a constant pitch, it's normal to see moment-to-moment changes of 4 or 5 hertz in the reading. Most of the time, the AF mode will work just fine. But there can be times where it's better to lock the decoder to a specific side tone frequency. The Control plus F key combo cycles back and forth between fixed frequency and auto frequency. To set the fixed frequency value, start in the auto mode and tune in a station, preferably a reasonably strong one, and adjust the tuning to get the frequency you want. When there, use the Control plus F key combo to switch to the fixed frequency mode, and that will lock that frequency in. And by the way, if this is what you want at startup, use Control S to go to the settings screen and tab down to the save button. Hit the enter key, and next time you restart, the decoder will come up in the fixed frequency mode with the frequency you just selected. Now, back to the alternate decode modes. To be clear, if the normal mode doesn't yield perfect decoding, it's not likely that the other modes will either, but one will often do better than the others. Here, experience helps, and to be honest, if your expectation is to use this without any CW familiarity, you're likely going to be disappointed. Although with good signal conditions and the far end using a keyboard, it can work pretty much just like any other digital mode. And in many ways better than most, because as a rule they don't support QSK, but that's just my opinion. To someone new to CW, the other advice I would offer is listen around a while before attempting to call CQ. CW ops as a group are about as forgiving as you could hope for, but because the mode itself is labor intensive, especially when sent with a straight key, CW ops tend to use a lot of shortcuts. So you'll thank yourself if you first spend a little time reading the mail on other QSOs and becoming familiar with the pattern of exchange, be it a RAG-Chew QSO or a POTA contact. With experience, you'll see that the decoder pretty accurately translates the incoming signal into the character sent based on more spacing standards. So take the time to get a rudimentary grasp of CW. That is, dada is an A and .it is an N. Then you'll pretty quickly recognize why the display reads like it does and can often unscramble mangled text as it builds on the display. But without the benefit of hearing and watching it develop, the same screen when viewed cold turkey can look like gibberish. Let's wrap up this video by looking and listening to the 4 decode modes in action. Rather than reviewing them in index order, I'll show them in the order I use the most. And since we've been using the NRM mode to demo everything else, I'll skip to BG2, the mode I go to when normal seems to be taking more hits than signal strength would suggest. BG2 settings allow for longer letter breaks and uses a little deeper pattern search to convert symbol sets to text. Watch and listen as text appears using BG2. BG1 is good when the far end exaggerates the inner element DA spacing to the point that the interval would normally be treated as an end of character state. BG3, I call it the cootie key mode, is tailored for ultra-short inter-element timing. For comparison, here's what W1AW looks like, and here's what the signal you're hearing looks like. To be honest, this example isn't extreme as some heard, where spacing is little more than a click between key down intervals. When using BG3, the state 5 detection is disabled and the tone detector is locked to fast sampling. Okay, let's stop here. I hope the video was useful, and if you do build it, please let me know how it worked out. As always, thanks and good luck with your next project.